In the previous videos, I described a set as a logical boundary, not merely a set being a container which holds the objects. We've talked about the logical boundary creates and the involvement of the predicates, right? And a set determines for every possible object whether the object actually belongs to this subset or does not belong, right? And basically, that's where that logical boundary part comes into play, because we assign each one of those values in the universe to be true or false, depending on the membership conditions. So, the identity of a particular set definitely does not come from the order we have. So, the way you order the elements, assign the elements into positions, it does not matter. And the name you give to sets also don't matter, right? Because you can see clearly in this little example, these are basically the same thing. A is the same way of saying B, but in a different language, okay? But the meaning is still the same, right? So the identity of a set comes in entirely from the membership structure, and we call that the axiom of extensionality, right? And I don't know if I wrote here. Oh, yes. And this is what the axiom looks like, right? So in order for you to say that two different looking sets are equal to one another, you need, you basically need the same exact elements on each side. So exactly when they contain the same exact elements, that's when you know that we have the same the same sets. Okay? So it's all coming down to the membership conditions one more time. Okay? So here we have, again, two sets, and we have a universe containing many possible objects, right? So set A classifies every object to be either 1 or 0, depending on, again, the membership conditions. Same goes for the B. Okay? Nothing crazy here. All right, and this makes them the equivalent. If they have the same exact, truth values, the same exact logical boundaries, that just makes them equivalent, right? So let's just get to the proof on how do we actually prove this. So we're just letting these two sets to be something with the predicates, where x is an element of the integers, and x is just an even number, and b is just 2k, where k is just a random integer value. So first, in order to start this proof, we're going to start I'm saying that there is this arbitrary integer called x, and this x is an element of A. So there is this, so that means that A is just a set. This is not an empty set. So, and by definition of A, that means that x has to be even. And also, by the definition of an even integer, the way you actually define an even integer, x is 2k, where k is just an integer value, right? So, and that is exactly what the condition requires for x to belong to b. So, therefore, you can simply state this implication on this order, because again, the order kind of matters here. And this basically means that A is a subset, the proper subset of B. So that means that A lives inside B. Okay? So this is only just one half of the proof. Because since we're trying to prove that A is B, we have to do two sides of the implication, because an inequality is basically a double implication, right? So A equal to B is essentially this, and the opposite has to be the same as well. And again, implication is not commutative. So that's we have to work the other way around, right? So this is the second part where we're going to let that arbitrary element be part of B now. So we're starting out with B. And by the predicate I stated over here, it says that x is 2k, where k is an integer value. Therefore, we're going to use a definition of an even value, an even integer. That basically means that x is an even number. And we go back and see the predicate of A. See, x is even. So that means that x is an element of A. Hence, you could say that these are two ways of, just for this half of the proof, yes, the implication would be this way. X is an element of B implies to x being an element of A. So now we figure that B is a subset of A. And since both of those cases are true, means that they're both subsets of one another, that means that they're equivalent to one another. Or, in other words, the logical boundaries, the logical condition of both A and B, they are the same, even though the name of the sets are completely different. And again, the order doesn't matter when it comes to stating the elements of these sets.